Hello. The initial quote today comes from Professor Andrew Short, 1999. Beaches are a part of the natural environment that most people know of and many make special trips to visit. They are a preferred site for much tourism recreation and residential and vacation development. As such, they attract considerable attention and pressure for development. And another quote from Professor Andrew Short is beaches occur on all sedimentary shorelines exposed to waves. They are amongst the most dynamic physical systems on the Earth's surface and occur on coasts wherever sufficient sediment for the waves to deposit it above the sea level. And this map again. Lujandyk and his collaborator in 2018 used almost 2 million satellite images to classify the state of the world's beaches in a very relevant effort. They have figured out that 31% of the world's ice-free shoreline is sandy, and this is a good approximation to the percentual number of the world's beaches. As we saw, 35% of the Asian coast is sandy, 32% of the Oceania coast is sandy, 67% of the Africa coastline is sandy, 23% of the European coastline is sandy, and 33 in North America, and 27 here in South America. Other important information is that beaches occur in all latitudes, in all tide ranges, and in all climates, and may be composed of all grand sizes from sand through boulders. Beaches are defined as accumulations of unconsolidated sand or gravel, reworked and deposited by tides, waves, and wave-induced currents along marine, lacustrine, and estuarine shorelines. Beaches are a highly variable natural system that can range from wave to tide dominated environments and from open coast, linear sedimentary beaches to perched beaches on rocky coasts. From a morphological point of view, beaches can be split broadly into two dimensions: the horizontal or beach plane view dimension and the cross-shore beach profile dimension. Let's see both of them. The beach plane view permits us to analyze and classify beaches in several ways. One of them is about their exposition condition. Beaches can be exposed to the open sea and receive, almost with no interference, all the energy propagated along the ocean. Beaches can also be semi-exposed with some headlands or islands or artificial structures protecting them from some part of the incoming wave energy. And beaches can also be sheltered or protected by headlands or inside an estuary, in some cases with minimal interference of ocean waves. The pattern of semi-exposed beaches and sheltered beaches are typically associated with promontories or rock stretches that reach the sea and segment the coastal strip, also known by several other terms such as pocket beaches, zeta bays, crenulate-shaped bays, spiral beaches, curved beaches, hooked beaches, headland bay beaches, structurally controlled beaches, among others. The main morphological characteristic is its plane shape, conditioned by the rocky promontories' presence and their relative position. The geological antecedent structures control beach processes such as coastal sediment transport and some of the waves' ways to reach the shoreline, like the refraction and diffraction phenomena. The orientation and plane shape of these beaches are controlled by the pattern of refraction of the waves. Some numerical or empirical models confirm this. There is for example, the logarithmic spiral shape proposed by Krumbane in the 40s and Yasso in the 60s, the parabolic base shape proposed by Su and Evans in the 1989, and then by Sylvester and Su in 1993 and 1997, and the hyperbolic tangent shape proposed by Moreno and Krauss in 1999 and developed by Martino and his collaborators in 2003. Here are some examples of these models that, in general, investigate the structural control geometry and try to quantify their effects on coastal processes. Unfortunately, we have no time for this today. This is the beach profile and some of its components. At first, there is the foredunes, the berm, the berm's crest, the scarp, the beach face, and the surf zone. And here we have the berm, the scarp, and the beach face. At this one, we have the storm weather berm, the fair weather berm, and the beach face. In two dimensions, beaches consist of some sequential systems grouped in three dynamic zones of wave shoaling: the surf zone, including wave breaking, and the swash zone. Each zone has a characteristic and resulting morphological response and shape. This image, adapted from Svensson and his collaborators in 1978, shows us the shoaling region from the wave base, a half of the wavelength, to the breaking point. At its seaward limit, waves begin to interact with the seabed sufficiently to entrain sediment and move it shoreward. Then, the surf zone is divided into the outer surf zone and the inner surf zone. In the outer surf zone, depth-induced breaking commences with the largest waves breaking with waves undergoing rapid wave shape changes. In the inner surf zone, smaller waves begin to break, and typically the majority of the waves are broken. In this region, wave shape changes are less rapid, and the waves often resemble periodic bars. The inner surf zone ends at the point where broken waves from the surf zone collapse on the beach face, driving swash. The spatial extent of the wave shoaling region, the outer and inner surf zones, and the swash zone vary with beach type and gradient. Beaches can be quite diverse, and the reason is that there are so many combinations to account for. Many authors used some ways to classify beaches, and a few of them we can present here. For example, by waves, we can talk about high energy and low energy environments like did Davis and Hayes in the 1984. We can talk using the annual wave climate for east or west swell or north or south swell. We can talk about the seasonal wave climate, the summer profile, the winter beach profile like Eman and Phillips in 1984. We can classify beaches using his tidal characteristics like macrotidal, microtidal, mesotidal, like Davis and Hayes in the 1984. We can also use some of its granulometry characteristics like a cobble beach, a pebble beach, or a sandy beaches. The mineralogy of the beach materials like those originated from quartz or carbonate. And we can talk about the global beach position by the climate and latitude, maybe polar, temperate, tropical on high, mid, or low latitudes. A general beach definition is a terraform sedimentary deposits formed by the wave action in an area established between the maximum depth of sediment mobilization in the submarine zone and towards the coast until the wave's maximum spreading effect. The closure depth is the maximum depth of sediment mobilization by waves. This graph shows some correlation between the seabed topographic changes and its depth of occurrence for beaches and nearshore zones in Australia, New Zealand, and Denmark. As we can see, the curve of changes in the seabed increase exponentially below 15 meters of water depth. And from this, towards the coast, depths can vary up to 4 meters and maybe even in a few hours. At the other end, the upper limit of wave uprush or swash is often the point where permanent vegetation appears, or an actual cliff base is evident. Early studies on beach dynamics were based on two-dimensional beach profiling. According to observations compiled by King, 1972, firstly, beach slope increases with larger sediment size and decreasing wave energy. Secondly, wave conditions during energetic or stormy seasons result in the formation of narrow, eroded subaerial beaches with gentle nearshore buried morphologies, whereas during calm conditions, a bar is attached to the beach face, resulting in steeper barless profiles. Using this knowledge, classical literature has tagged these two end members as summer beach profile and winter beach profile. In two-dimensional beaches, there is a seasonal movement of nearshore sands, and then we can recognize the summer beach profile and the winter beach profile. The summer beach profile presents the beach with a high stock of sediments, sands, originating from the outer surf zone, gradually mobilized for periods of good weather with waves of low slimness. In the winter profile, the beach has a deficient stock of sediments that have been undermined and transported to the outer surf zone for a destructive period, eroded by storm waves. Also, in the two-dimensional beach model, we can make a comparison between summer and winter beach profiles. The depth of closure is that position in which there is no effective mobilization of sediments and no change in general beach topography. And during extreme events, when storm waves are associated with strong winds and high spring tides, this leads to a significant increase in sea level, and the result can lead to the complete disappearance of the beach. Also, regarding the idea of summer beach profile versus winter beach profile, not to mention that all the beaches exhibit wave climate seasonality and that also storm conditions are not necessarily related to winter seasons. It would be desirable to label them respectively as calm or as a swell beach profile and energetic or storm beach profile. Anyway, these configurations attest to two different morphodynamic regimes. On steep beaches, waves break directly on the beach base and run up the more vertical beach face, returning as a strong backwash, which returns seaward as a reflected wave. Therefore, this beach configuration is referred to as a reflective beach. At the other extreme, on gently sloping beaches, the surf zone is more expansive. As waves propagate to the shore, their energy decreases by viscous effects in the sandy bottom and eventually breaking. These beaches are referred to as dissipative beaches. Considering those ideas of the summer beach profile, the winter beach profile, and their configurations of wave energy, some authors developed the surf scaling parameter. Was developed initially by Carrier and Grispan, 1958, then Guza and Bowen, then Guza and Inman in the 1970s. The surf scaling parameter E equals the alpha y, that is the wave amplitude, that multiplies the square of omega, that is 2 pi under t, where t is the wave period, under g tangent, the square of tangent b, where g is the gravity acceleration and b is the mean wave slope. So in this parameter is considered some indications of wave, like height and period, and some indications of the slope of the beach, how these interact and how they promote changes. More specifically, these parameters shows a correlation between wave energy characteristics related to the bottom morphology. And with that, for E values, we have E lesser than 1, there is a complete reflectivity and no dissipation of wave energy along the beach. For E lesser than 2.5, there is a strong reflectivity and resonance despite the reduced dissipation of wave energy. For E above 2.5, the waves start to break before reaching the beach face. That is, the wave energy begins to be dissipated in the surf zone. A gradual increase in E accompanies a gradual increase in the width of the surf zone and in the energy dissipation of the waves until they reach the beach face. For E above 20, there is complete dissipation and no reflectivity. In summary, reflective conditions occur if E is lesser than 2.5 and dissipative conditions prevail when E values are above 20. For E values ranging from 2.5 to 20, then both reflection and dissipation processes operate along the beach profile. These conditions and the resulting morphological configuration are referred as an intermediate beach. This model, when applied to a sequential time series of beach profiles, reveals a successive beach profile change, an erosion and accretion sequence that is entirely driven by waves. The secondary morphological features as bars, runnels, cusps, troughs are also strongly related to the wave climate and to sequential configuration of beach profiles. Sequential beach profiles are a monitoring technique that can access beach morphology changes using topographic methods. Here are two examples of using a pier as a support. The maximum vertical oscillations in these beaches were found inside the surf zone, where the daily movements of sandbars promoted vertical changes up to almost 3 meters. Sequential beach profiling can, for example, illustrate and quantify those multivariate associations that characterize dissipative beaches. Here is some example of one of our monitored beaches in southeastern Brazil. And in this other example, also here in southeastern Brazil, the sequential beach profiles can be superimposed, and this envelope of beach profiles can keep up with those submerged bars and troughs in order to clearly understand their dynamic. This configuration and these submerged bars disrupted by rip channels are typical of intermediate beaches. In this one, also in southeastern Brazil, beach cusps and beach step morphology tend to appear in reflective beaches. Although beach cusps cannot be properly assessed using sequential beach profiles, the steep morphology and the more restricted beach envelope are clearly indicators of this type of reflective beaches. The transition from one secondary morphological configuration to a different arrangement also depends on the antecedent beach profile and wave conditions. This statement is especially critical for intermediate beaches, and at this point, their study and characterization cannot just rely on a two-dimensional approach. Thus, we need more. Different types of nearshore bar morphology and rip channel patterns result from wave conditions and, to a lesser extent, are influenced by the nearshore slope. Therefore, there is an inherent three-dimensional behavior of beaches and their surf zones. Water motion in the surf zone is driven mainly by breaking incident waves. Subsequently, standing infragravity wave motion and quasi-steady currents result in sediment transport at different frequencies and directions. Nearshore bars appears in areas where sediment transport converges, and bar troughs form where sediment transport diverges. Professor Andrew Short, 1979, collected 18 months of daily observations along different microtidal beaches at New South Wales in Australia and classified the full range of three-dimensional beach and bar types on a selected combination of wave dynamics characterized by Wright and his collaborators also in 1979. Here's the original paper, Three-Dimensional Beach Stage Model from Andrew Short. The main contribution of that work was to relate the end member and the transient three-dimensional state of the beach profile configuration through sequences of increasing and decreasing incoming wavy energy and sediment size coarsening or thinning. The three-dimensional beach stage model recognizes the occurrence of distinct beach morphologies or beach state, and the wave climate is nowadays a dominant paradigm in coastal science. So the Australian model of beach morphodynamics recognizes six distinct stages or states of beaches: the dissipative, the intermediate that can be underclassified as longshore bar truth, rhythmic bar and beach, transverse bar and beach, ridge and runnel or low tide terrace. And then the last one is the reflective stage. Those six stages were defined on the basis of the dimensionless fall velocity, first developed by Gurley in 1968 and then by Professor Dean in 1979. The omega parameter equals the wave breaker height over omega s that multiplies t. Omega s is the sediment settling velocity and t is obviously the wave period. Then if the parameter is above 6, beaches present a dissipative state. If the values approximate equals to 5, there is the intermediate longshore bar truth. If it's approximate equals to 4, there is the intermediate rhythmic and bar and beach. If omega approximately equals to 3, the intermediate stage is transverse bar and rip beach. If approximate equals 2, there is the intermediate low tide terrace or ridge and runnel. And if the values of this parameter are below 1, the beach tends to present a reflective stage. So decreasing HB and increasing T and omega S promotes reflective beaches, whereas increasing HP and decreasing T and omega S favors dissipative beaches. These models succeed in explaining spatial differences between sandy beach environments and also in predicting beach morphology changes according to gradients in wave energy input. In general, for a medium sand size beach, breaker wave heights lower than 1 meter would lead to a reflective beach domain, whereas break wave heights of 3 meters will move the beach to the intermediate dissipative beach stages. And all of this information can be shown in this sensitive plot that illustrates the contribution of wave height, sediment size, and wave period to omega and beach states. In order to identify the beach state, the intersection of grain size and wave height is determined first, and then the wave period. Take a closer look at this graph. See if you can understand it clearly. Now now some of the main characteristics of the dissipative beach stage. Waves tend to dissipate energy throughout the surf zone. Progressive type wave breaking. Low declivity of the beach profile. Fine or very fine grained sediments. They occur on exposed beaches. There is the presence of several narrow bars and rails, an extensive surf zone above, mostly above 100 meters, and the beach profile has little variability or greater stability. And now some of the main characteristics of intermediate states. Firstly, the longshore bar through state. There is a pronounced bar parallel to the beach and separated from it by a longitudinal parallel and deep trough. Fine and medium grained sands. In the bar, the breaker type are plunging and slow tide, and there is the development of well-spaced return or rip channels. In the high tide, the breaker type is progressive and the waves tend to be collapsing breakers in the beach face. Through depth approximately 2 to 3 meters, weak and medium longitudinal currents, especially at low tide. And now the second intermediate beach stage is the rhythm bar and beach. And they present the rhythm of the beach and detached bars. The rhythm of the bar separates rip channels, plunging breakers on the bar with rip currents spaced rhythmically between 150 and 300 meters. There are smaller and shallow waves after the bar, however, deep flows and currents in the channels. And now the third intermediate state is transverse bar and rip. Bars are shallow and transversal to the beach, separated by return channels, spacing normally between 115 and 300 meters. Waves break in the bar, which is stuck to the beach and is shallow and usually planar. In the depression or in the trough, the slope and depth increase, inhibiting the wave breaking and forming strong longitudinal and return or rip currents. In this intermediate stage, the low tide terrace or bridge and runnel is the stage closest to the reflective one. Shallow terrace or bar, which remains exposed during low tide, occur on exposed and semi-exposed beaches, however, in a regime of small waves. There is the presence of medium to coarse sands, development of weak and localized return rip currents, commonly in small cuts on the terrace or bar. There is a sharp medium declivity. The bar or terrace is exposed at low tide. In high tide, the wave breaking occurs. Then the last one is the reflective stage, that waves can tend to reflect their energy directly on the beach face. It is usually associated with low energy environments. There are collapsing or acceding breaker types, the steep beach profile, medium to coarse or very coarse grained sized sediments, usually occurring on protected beaches, non-existent or undeveloped surfing zone lesser than 5 or 10 meters, and the beach profile with little variability or greater stability. Let's see the final examples. In the three-dimensional beach stage model, considering all of those six stages as they were described, in nature, sandy beaches exist in a continuum spectrum of states. The dominant state, where the beach mostly resides, there is the beach modal state, is dependent on the modal wave climate and sediment size. Change in the beach state is dependent on how much particular combinations of wave height, period, storm direction, duration, and frequency, the concept of storminess, occur on the beach. And from the dissipative to the reflective, there is a decreasing wave energy, and this is so called the accretion cycle. And in the other hand, from the reflective to the dissipative beach stages, there is an increasing wave energy that is so called the erosion cycle. Let's see some more information about both of them. In the accretion cycle, there is decreasing wave energy. The accretionary sequence begins with the high energy dissipative beach state, moving down through the intermediate states, finishing at the low energy reflective beach state. Dissipative states are temporary, elusive except in areas with fine sand which are exposed to waves larger than 2 meters in height over weeks to months. Often, beaches reach this state after storms and quickly evolve to more intermediate configurations just after the event. Now let's see two videos at the same beach, that is Massambaba Beach in southeastern Brazil. Those videos represent two very different wave conditions. And then in the erosion cycle, there is the increasing wave energy and involves the coupling of large waves with water volumes moving in and across the surf zone. When large waves reach the shoreline, they move sediment seawards, flattening the beach slope and widening the surf zone. When a reflective beach state experiences an increase in wave height, plus than half a meter, waves and currents reorganize the sediments in order to accommodate the beach to the new higher energy conditions. The eroded sediments form an incipient subdued bar that causes the wave to break further seaward, enlarging the surf zone. And again, we are going to see two videos on the same beach to illustrate the erosion cycle. And now some final considerations about the dissipative to reflective continuum, including this idea of accretional and erosional cycles. Professor Wright and his collaborator in papers published in 1984 and 1985 have shown that the rate of change between beach states under an accretional sequence or trend rarely reach the transition from one state to another per day, whereas changes during the erosion cycle can be faster than one beach state per day. However, if waves are more or less constant, the state of morphological arrangement can be maintained and no change occurs. Therefore, longshore topographic variability may be faster on swell-dominated open coasts, since the arrival of long-period swell waves after a storm can accelerate the variability of beach states. And this is enough for today. See you soon. Take care and be safe.